Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is Transformer Condition Assessment through Online Partial Discharge Monitoring. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. Mihai, if you could switch slides for me. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, your certificate of attendance, copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Mihai Huzman. He is the PDIX Managing Director. Also, to assist with the question and answer session, we will have joining us Marcus Soler, PDIX Managing Director, and Charles Nybeck, Applications Engineer. All right, let's go ahead and get started. Thank you so much for joining us today, Mihai.
I'm very pleased to have everyone on board, and thank you so much for attending, making time for us. Today, I would like to speak a bit about partial discharge monitoring on power transformers. Probably at the beginning, we should talk a bit about why partial discharge is an important phenomenon on transformers, what's happening. I would like to maybe even have here a nice little logo for some people that they are acquainted with the world of partial discharge. This is the PQN diagram, and use it as sort of a placeholder throughout to be able to remind us all that we are looking at very interesting physical phenomena that are influencing the life and effectively the functioning of our devices, in particular power transformers. So transformer failure, as we all know, can be very costly. I was just until about an hour ago in Siemens, and we were looking at some of the tests that they are doing there. And there is a plethora of testing that is being done in the factory in order to make sure that the power transformers are up and running. They are very good, very functional, and of course they will never create problems in the field. But of course, this is at start when they are first conceived, and definitely the power transformers have a life of their own. And maybe here you can see a dramatic example of such a life when there are issues generally caused by the quality of the insulation within the power transformer, by problematic manufacturing, and of course that can lead to specific explosive gases being built within the tank, even within the bushings, etc., and then explosions can occur. If we look again at the life of a transformer, we can speak about the typical bathtub curve that starts with the beginning when the asset has a very young age, and of course then there is a period of life when, generally speaking, nothing happens, and then towards the end of life, 30, 40 years depends, we need to pay special attention because the wear out and the failures can be more prominent. Where do these failures come from? Generally speaking, you can see a large portion of these failures coming out of insulation type problems. Of course, there are coolant, there are winding, there are core, there are cap changing problems, there are bushing problems, but a large proportion, over 41%, comes, statistically speaking, from insulation type problems. And so definitely paying attention to this topic, to insulation, is mandatory. And how do we do that? Generally speaking, we can look at a partial discharge monitor. This is happening right after the transformer has been built, may not even be filled with oil yet, and partial discharge is being tested at different levels, even on components. And of course, after that, you go through very complex tests. I've just been today with our devices, in fact, even with our truck from PDIX into the Siemens factory performing such type of tests. Early failures due to improper Hfct, transportation, on-site commissioning can be possible. Of course, people put various sensors on these transformers to make sure they arrive at destination in proper form and shape, but nobody can guarantee that. Also, there are situations in which a transformer is being assembled at site, and that's another moment when it's very important to perform proper testing. There are random failures, generally speaking due to high load or maybe some atmospheric problems, including lightning or high temperatures. And so during the life of a transformer, we can see potential deteriorations of insulation and aging of materials, and all that can play a significant role in terms of failures. So, as a result, one way to monitor the insulation characteristics of a transformer is actually through partial discharge. And so when we look inside of a transformer, maybe after some problems have occurred, or at the moment when tests are being performed, we can see sometimes problems with the materials, the quality of these materials, paper in particular. We can see maybe some design-related issues. We can see some humidity in oil. Of course, once the transformer gets filled in with oil. The usual phenomena, as you know, is that problems with the insulation, particularly with paper, generate certain gases, and these gases are effectively explosive gases, acetylene, methane, and so on, and those can cause significant issues. The impact of partial discharge on transformer insulation can have a different level of severity. In fact, during the acceptance testing, both factory and site, there are certain predefined limits for the partial discharge that can occur at different voltages for a certain amount of time, etc. All these are specified in IEC type norms, and that's how all transformer factories are testing their devices. But again, during the life of a transformer, there are accelerated degradations of such insulation materials, and of course, this can lead to reduced life expectancy. Clearly, the worst case scenario is when there is a breakdown, and then a blackout can occur. And that's why people should be looking at doing online partial discharge monitoring all the time, throughout the life of a transformer, especially on critical assets. And critical assets can be of two sorts, can be expensive assets. You know that 200 MVA transformer can be 5-6 million euros at least. And at the same time, you can have a small transformer, maybe 40 MVA transformer that is placed in a key factory, or it's a step-up transformer of a nuclear power station, etc. So all this is a big issue. The problems that I can see reflecting in transformer life are basically various, and I'm just going to give you here some examples about common root causes, how the partial discharge can appear, where usually we can see such problems, and again, we can effectively see the eventual deterioration of the insulation. So sometimes there are inadequate stages prior to impregnation. Sometimes maybe the transformer is not sufficiently dry before the oil is, before the paper insulator is impregnated with oil. Then sometimes there are remaining conductive particles in oil, and there is a water problem. There are some electrical connections. There are floating static shields. There are maybe poor contacts of the tap leads at the oil to sea tap level. The online tap changing device. And of course, there are sometimes drops or glue of some other elements in areas with elevated electrical field, and these can, of course, create partial discharge. Partial discharge in many cases is measured in picocoulomb, and therefore we have developed devices that can measure that. The online monitoring of power transformers and accessories like bushings, in my view, is essential because, of course, at the time when the transformer is being manufactured, proper tests are performed, data is being recorded, and that represents, let's say, a starting point. But then the transformer goes to various stages, and it's very important to record the trends. how, let's say, the partial discharge evolves through time. And therefore, the trending and the changing patterns are very, very important to be recorded and looked at because they can indicate incipient failures. The analysis of such patterns can further down the road assist with potential investigations. Equally, depends on what kind of sensors are being used on the transformer, location of such partial discharge or partial discharges can be identified. So the added value for partial discharge monitoring is definitely when this is being combined with DGA, with time delta, with temperature, with load monitoring. Of course, transformer, based on its criticality, as I discussed, can be loaded with all these sensors. Of course, these sensors have a cost. So then there is an optimal ratio between the cost of the transformer and such sensors. And I would say that optimality is given by the criticality and the price of that particular asset. So people will choose to implement different methods. But for instance, if you or somebody installs a DGA device, the dissolved gas analysis will only show things after a while. With partial discharge monitoring, things can be shown even earlier. So there is a discussion. Of course, it depends on how much money people want to spend on that transformer or monitoring that transformer. But my particular advice after working in this field for a while is to actually have partial discharge combined with DGA, combined with time delta, and so on and so forth. But partial discharge can give a very good initial quality and quantitative measurement of what's happening inside of the transformer, inside of its tank, inside of its bushings, etc. So some of the technical details I want to show, how this is being carried out, partial discharge monitoring, and then I will look more into features, benefits, and show you some of the references. So obviously, partial discharge, at least at lecture level, it's a breakdown of a small area within a certain insulation gap, and each pulse will generate different but measurable electrical signal. Usually, this electrical signal, as I mentioned, is measured in picocoulomb. It's a pulse, it's an electromagnetic pulse, and that also generates a UHF type signature. And of course, sometimes this pulse can differ and generate an acoustic, generally speaking, in ultra high frequencies. And so, with adequate sensors that are looking at the local displacement pulse, at the electromagnetic pulse, at the acoustic pulse, we can detect and then even locate what's happening within, let's say, the main tank, within the windings of the main tank, within the insulation of the windings of the main tank. So these are different examples. So you can see an electric PD pulse taken from a test tap of the bushing. You can see an UHF pulse taken from an antenna that is placed through the oil valve. Or you can see an acoustic signal measured by placing sensors on the tank wall. What is very interesting is to actually have all these sensors and monitor all these channels, because the bushings are important, what's happening within the tank is important, and of course acoustically we can even locate which areas are problematic if we decide to actually do service on that particular transformer. So how do we deploy basically such sensors? If you look at the entire transformer, you see that at the top we have the bushings, and there we have the capacitive cap, the cap that we have basically designed special fittings. We have for a variety of such bushing fittings. There are a variety of companies that are purchasing from us such fittings because they would like to connect instruments to the bushing. There are companies that they are purchasing such fittings just to actually be able to read what's happening with the bushing, but most of the people will continue by installing the box that you see here connected to the Teflon cable. And this box is able to split voltage and partial discharge measurements. So we can look at time delta measurements in relationship to that bushing. We can look at the characteristic of the bushing. from, let's say, a pure electrical point of view, but also we can look via partial discharge at the insulation. Now, what's happening inside of the main tank gets propagated through the windings, through the bushings, and then, therefore, with such a device can be read. Now, from this little box that you see right by the bushing in the central picture there, of course, information through an RJ58 cable is being drawn into a cabinet, and within this cabinet there is an ICM monitor that sits there and actually reads the information in the right frequency and for picocoulomb transfer from the bushing tab, but can equally do it from the oil vane antenna, UHF antenna, or from even acoustic sensors that are placed on the wall of the transformer. Many people, including Siemens, including Conchar, including GE, they are buying such sensors from us, and of course the monitoring system, because they are asking various tenders to offer a complete system, including partial discharge monitoring. The boxes that we have also another characteristic. They can do noise gating, and this allows for several things: to actually suppress unwanted noises and to extract the proper PD pattern and trend across time. We are making records of these patterns. We are able to show them across time, and this can give to a specialist the right understanding of what's happening with this particular or with a particular transformer. Now, what I would like to mention here is that many people choose to have this system with, let's say, an alarm mode trigger, and then when the alarms are above a certain level, specialists are going to dial in and look in detail at the patterns in order to understand what has happened with the transformer. The typical signal processing of PD signals is split, I would say, into the AMP and SPEC mode. In the AMP mode, we are looking at a particular low pass plus a gain, followed by a high pass and a gain, and then we do the peak detection and we pass that through an 8-bit A-to-D converter. When we want to look at the spectral mode, we basically do a low pass with a central frequency of about 1 megahertz. We follow that with a gain. Then we have a filter, and after that we use a bandpass filter and the peak detection. Again, all that is analog, and then we follow that with an A to D converter in order to bring everything to the digital mode. And we have also the option of using a sync with auto gain, and then there we use the 12-bit converter because we need to know exactly for AC where are the zero crossings, to understand exactly the frequency and do proper synchronization. Within the transformer, you can see now a section where you see the main tank, you see the bushing, and if you look, you basically have a simplified block line diagram that looks at the transformer, the calibrator, the bushing, and the decoupling unit. So something that I haven't mentioned now was this business with the calibrator. So before, and in fact even during the factory acceptance test, the calibrator is used in order to calibrate for a certain level of picocoulomb partial discharge. Usually they look at 100 or 200 picocoulomb, they inject that to the bushing, and then of course they want to read the same amount through the bushing tab, and eventually the instrument should be able to do that. And so, in order to do that, certain calibrators are being sold and used in order to properly do the test. Further down the road, I touched upon the fact that we have many bushing adapters. These bushing adapters are actually built here in Aachen by our folks in PAX and have been designed for a variety of bushings. Folks from ABB, Passoni, Villa, French, GE, you name it, are buying such kind of bushing adapters from us. And there are multiple designs. They have a proper robust aluminum aluminum enclosure. They are nicely engraved. They can be basically in action for many years. And I have seen pictures myself, or I've seen them on transformers. where you know exactly where and when they came from. There is a serial number associated with it, so they are very well designed. And also they are designed to be operating on a very extensive temperature range from -40 to 90 degrees Celsius, plus 90 degrees Celsius. Of course, they are IP65. And all that is very important because, as we know, these transformers live in a variety of environments. They are exposed to the weather, and therefore the bushing adapters have to last forever. The decoupling unit has basically a quadrupole typical feature, has a voltage output via capacitive divider, has of course the PD output, has two N-type connectors and the same type of protection and temperature range because it needs to be outside, generally speaking, with a short lead by the bushing coupler that you've seen previously. The entire housing is stainless steel and it's also aluminum. Based on whoever chooses to install them, they have different preferences. The typical, I would say, cases that we sell and I've seen on many transformers are actually the aluminum housing. Now, we are also producing Uhf sensors, basically TVS2 and TFS1. They are introduced either through the oil valve, through the drain valve, sometimes through the filling valve, but mainly through the drain valve. And also there are hatches on these transformers, so we build such kind of Uhf sensors that they are mounted straight on the hatch. Here we have a very good collaboration with a variety of transformer manufacturers, and therefore we are able to know ahead all their drawings and therefore produce the right flange for the corresponding tank or for the corresponding valve. The sensor itself has a built-in logarithmic Uhf signal converter, has a range from 300 megahertz up to 1 gigahertz, has the typical TNC output connector, and of course the one that is used for valves is an oil type design. It's being introduced exactly based on the transformer specific manufacturer specifications into the tank in order to avoid any potential issues with getting too close to the windings, etc. The cables are also special cables. They are Teflon cables. They are designed for wide range of temperatures, very heavy weather conditions. This is a very important element. You will not believe it on other manufacturers how many of these cables I've seen failing. We have a recommended distance from the VCU to the ICM monitor, which is about 20 meters, but generally speaking, even on large transformers, that's plenty. The CTV2C provides also a protected ground, and of course these cables can go into a junction box that is shown. So both ends of the cable sometimes can be protected with additional ferrite clamp-on cores in order to avoid disturbances. Generally the cables are 50 ohm, and as I mentioned, for a wide variety of temperatures. The antenna is an exterior antenna that picks up noise pulses radiated, generally speaking, by corona. They are high frequency current transformers, CP1 type or CP100, that they are picking disturbance pulses from shields, of signal cables, or from ground connections. I'll be honest, mounting such antennas represents a tricky thing because obviously they will pick up a wide variety of signals. So generally people prefer to have the bushing couplers and also the hatch or oil valves for UHF signal. But this antenna is a noise gating tool and it has its own benefit when employed in conjunction with our devices. And now we should speak a bit about the Acquisition Icm Monitor. There are 4, 8, or 12 multiplex channels. In this case, you see an 8-channel device, a 4-channel device with a C, but the device can grow. In this case, it's a half rack device, 19-inch rack device, but can be bigger and more channels can be added. It has a separate sink and gate output, and from the perspective of the device itself, it has the LAN, the USB, and of course separately it has the IEC61850 port. We are customizing such kind of ICM monitors. I've seen them packed into IP66 boxes. I've seen them definitely with a screen or within, let's say, an outdoor camera. But there are many, many options, and of course for that I recommend that you speak with your sales representative to find a device that suits your needs. Various utilities like to go by the transformer and look at partial discharge patterns. Others prefer to be in the office. Others prefer in the substation building. The whole idea here is that signals can come out to say, man, I have a problem. And those come out through the IEC61850 port, or they can come out through binary relay contact. And once such signals are being issued, generally a specialist is being called, logs via the LAN. Of course, this LAN port can be transferred all the way to substation or even further into the network operation center. And there, the exam of all the patterns, PD patterns, etc., that you've seen a bit, and I will show more, is taking place. So the ICM monitor, as I mentioned, can be packaged in various ways. It's by the transformer, has a screen, has the ability to show a variety of patterns, the typical 51 diagram, black and white. Of course, once somebody logs in with a PC, will see that in color, has the ability to trigger alarms, and has the ability to aggregate data. So the Uhf measurements, the partial discharge, the acoustic measurements, all can come together into this IC monitor, and then of course based on the alarms issued, the information can be examined by specialists. In this case, you can see this picture, another type of case which has of course a screen, has a certain number of channels, has the LAN, and of course the annunciation, binary annunciation, and has also a common interface, RS232 interface. These are other examples where we are using steel cabinets. They have also a very nice marine name, TDMR 500. We've even installed them on boats, on other things, but for transformers, these are typical ways of deploying the device. It's a compact device, compact install, and of course inside of these stainless steel cabinets, basically a multiplexer can be mounted, a switch can be mounted. All the cabling coming from the transformer comes into these junction boxes and eventually into the ICM monitor. There are other ways to connect to the ICM monitor, which I will show you in a second. But before I get to that, I just wanted to show you a bit about the software and to explain that via remote access, multiple instruments can be viewed with our software. We can see the long-term trending, both in time domain, but also via the T2N diagram. Of course, there is the pattern acquisition is done in a colored fashion. To the device, it's possible to connect locally via USB or, of course, with a LAN. The LAN can be ported at long distance, or we can use even local computers to actually process information, and then you can export screens at the distance. So all this is possible. This is a typical example where a computer, now of course shown in this majestic desktop manner, but of course nowadays laptops are very common, is connected to the LAN port of the ICM monitor. All the functions are possible to the software, and the trending values, the PD patterns, the PD alarms, the spectrum, all this information is visible to an operator, to an expert. And of course, there is an EXC that runs the service mon-EXC, and that permits the ActiveX interface, which can be used for a variety of other applications. Another example is via 61850. So via 61850, all data sets and relevant information comes out. There is a specified stack that is being implemented, and of course, we provide those specifications and the IES file to whoever wants to deal with the IEC 61850 project. Mainly people are getting via 61850 the NQS, the QP, the alarm status, and after that they tend to dial in to see in detail screens that I presented previously. Another way to actually connect to the device is via this DCG 61850 module. This can be purchased, of course, from us. It connects into the LAN port, and eventually it generates 61850 information. Some of the monitors you've seen have a dedicated 61850 port, which you can imagine it embeds this DCG device, and this is just a matter of how people would like to see, how compact they would like to see the device, and we will help with the order. The provision of 61850 is done via ICD files, and there are a variety of scouts that can be used to actually look at data and make sure that the device generates appropriate information for the SCADA system. Another way to actually connect to the device, as I mentioned, is via direct LAN, via USB, via RS-232. Generally speaking, as I mentioned, because of the large volumes of information, the direct LAN is preferred. Locally, the USB. RS-232 communication is more used for enunciation in general, not necessarily to draw out PQN patterns from the device. Another way to connect to the device is to have an additional module, this LTE mobile communication interface, and CII1. And this interface effectively enables the device to be queried via an LTE network. There's no cabling, the UMTS provider, is going to give us a SIM. The SIM goes inside of this box, and then everybody that is, of course, entitled from a user management and cybersecurity point of view could look and draw data out of the device. Another way to do it is to actually have such a mobile web server, MWS1, which connects to the device, and after that, from a distance, a variety of people can use agnostic browsers to actually look into the monitor. This is the beauty of a web server, as we all know, and therefore specific data sets can be provided by the instruments to different users based on their rights. And again, this is always independent, web browser agnostic, and this is a very nice way to actually deploy the device. I've seen this being done quite frequently, especially when people didn't have a local network there, but also when they did, because they preferred this way of deploying it in order to allow several people within the substation to actually look at various subsets of data. The data management, of course, takes various forms, meaning that all the data is being recorded, can be retrieved, but we have developed also an ICM expert software, which has a database of patterns, and based on this database of patterns, pattern comparison and classification can take place. People can store photos, comments, effectively can monitor very effectively the asset across time. And the ICM expert can give a certain level of advice on what problems this transformer may have. And as a result, a specialist may dial in further, and we have plenty of people here that they can help you with that. So looking a bit at the PD monitoring, what are the features and benefits? I would like to point out that we have, as I mentioned, a variety of ways of looking into the transformer. We have the UHF, we have the acoustic modes, we have the spectral analysis, and these kind of sensors are very useful. But I will say that people will choose how many of these sensors they implement based on the value of this asset. The spectrum analysis is a suitable measuring frequency that can be selected at site via signal-to-noise ratio optimization. The gating input is used to reject external disturbances. You've seen that external antenna. This is a typical way of doing gating. We have a multiplex type device, which obviously makes it more cost effective. And we have a variety of interfaces. Also, the auxiliary 20 milliamp inputs can integrate our device with VGA, with oil temperature, voltage, and then all the information can actually be shipped out via our LAN interfaces, via 6150. So there are multiple interfaces, both local and remote, and of course, these interfaces are used to assess the data, the long-term data, but also instantaneous data. A PQ1 packet can be quite relevant after a while, after a number of pulses have been acquired. You can see quite well what type of installation failure you may have. Now, some comments on the UHF system. There are lots of UHF systems out there, and I have to tell you that just UHF systems are a bit insensitive to certain problems. I mean, they do not identify all the defects in the transformer. There are higher modes above the 300 megahertz, which are being attenuated. Sometimes it does not allow comparison with the factory acceptance tests, for instance, in relationship to IEC modes. There are no calibration available in terms of picocoulomb, as it's in the case of pure PD. And honestly, UHF sensors can be costly, and especially the oil valve, for instance, can be difficult to install. But this, in conjunction with, let's say, the bushing adapters and the acoustic, provides a very good image on what's happening within the transformer. When we basically discuss with a new customer, we have a very well prepared questionnaire that allows us to have a structured dialogue to understand exactly what you guys would like to have on your transformer, on your future transformer, on a current transformer. And of course, here the differentiation is made by the kind of sensors we can install for aftermarket, maybe different than for greenfield for a new transformer. Of course, the spec sheet, the manuals are all available. We have adequate certification both for our firm and also the calibration lab that we have here, DAX calibration lab, and definitely 6150 protocols. So for all these things, we have worked out together with our dealers, Conchar, ABB, GE partners, a very comprehensive set of documents, manuals, certificates that effectively give that safety and security to an end customer to make sure that they are installing a proper system. This is German quality, and of course, I'll be honest, it comes with a price, but at the same time, equally, you will not see problems in exploitation. They have very few devices, if any actually, that come back with little problems, and so we have a very good warranty program. And between all these things, many of our OEMs purchase from us, but also end customers, utilities, they come to us to install transformer monitoring devices. Since I mentioned some of them, maybe I should show you some of the references. So we have, as I mentioned, GE, Conchar, ABB, Siemens, Becca, the ESDI, so lots of key transformer manufacturers, but also people that they are making devices are coming to us to purchase, let's say, the partial discharge component. And this is very common here in Germany, I would say, where big companies like Siemens, like Audi, like BMW, and so on, they will allow, let's say, smaller firms like ours to be very innovative, very competitive, and they will come and purchase devices from such small firms in order to make sure that they are always getting the best quality device available on the market. So you have here our contact information. I would like you to basically send us both a webinar survey. That would be great if we can rate us. It will always help us to improve. It would be nice to know where from you heard about this seminar. It will be interesting to rate my effectiveness as a speaker, and of course the webinar content. The sales team from USA and Mexico is at your disposal both through their emails and through their phone numbers. Equally Canada sales. So I believe that lots of NAFTA people have dialed in and they will be able to take advantage of these numbers and ask further questions. Now, of course, during this session, we have an entire section dedicated to Q&A where we hope to get your interesting questions. And I will try together also with my panelists to answer them. So I think we got to that point, and Michael, I think maybe as a moderator you can help us further to navigate.
Yep, that's what I'm here for. So, as previously stated, our presentation portion of our webinar has officially concluded. We'll now take a little bit of time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's also a field where you can request a quote or a demo of any Megger products. A copy of this presentation, a certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. As a side note, I will be trying to clear up a little bit of that echo that we've been experiencing today on the recording link for those of you who'd like to go back and listen back. You can also view video recordings of previous webinars as well as register for upcoming webinars on our website at us.megger.com/webinars and register for our next webinar next week. So let's jump into our questions. Our first one I'm going to be sending over to Charles Nybeck. Charles, this equipment appears to be permanently installed primarily during construction. Do you have any portable non-permanent options?
Yeah, so at Power Diagnostics, we boast a large variety of instruments, both for offline and online measurements. As you saw Mihai covering monitoring solutions that were primarily installed during constructions, as you said, there are also, as you mentioned, the ICM Monitor. There is an ICM Monitor portable solution that could be used for non-permanent as long as you have your bushing adapter or your coupling units in your termination box that are already pre-installed. Once you have your coupling units installed and your termination box installed, you could then come periodically with your ICM Monitor portable or the ICM system and perform your online measurements at that point in time. So this was an example of permanently installed solutions, but there are also portable and non-permanent solutions or options as well.
All right, thank you, Charles. Our second question I'll send over to Marcus Solar. Marcus, on which level should we set warnings or alarm levels on such systems?
Yeah, hello everyone. Yeah, good question. Alarm levels, warning levels, that's always the questions when we commission such a system. We know from the factory acceptance test, a typical acceptance level for power transformer, oil-filled power transformer in a range of 100 to 200 300 picocoulomb, and we try to achieve this sensitivity in the field. So the first indication would be a level higher than this acceptance level, or a level higher than the warning level. So what we do, the noise floor level. So what we do, we calibrate the system in the field, and then we set the warning and alarm levels 30% higher than the noise floor, which should be much lower than the acceptance level that we know from the factory. It's the first indication. If we are measuring in picocoulombs, according to the IEC 60 to 70 calibration procedures, below 1 megahertz. If we go into a higher frequency and we measure in millivolt, then we do not have the comparison with the factory test. So here we have to set a level according to our experience, let's say, put it this way.
All right, thank you, Marcus. Next question going back over to Mihai. Is there any way of monitoring the quality of the contact of the bushing adapter, as a poor contact may produce a catastrophic result?
So again, we are testing very carefully these bushing adapters. They are made out of aluminum in the sense that they have a gold-plated contact, and then they have basically a seal, and they are properly screwed into the system. Now, I have to tell you that the voltage that generally is found at this bushing adapter is somewhere around 10, 15 volts, depends on the bushing. So when the question came about the catastrophic result, I think it's more about if the information doesn't get through or gets tainted, of course, the bushing adapter has a central role. But in the same way, the ICM monitor, in the same way, the box that is near the bushings, and I would say that the bushing cap adapter is basically a very well checked piece of equipment. Effectively, when the bushings are taken off power, there are measurements being carried out, and then we see exactly how well the cap adapter is functioning. But this is a pass-through.
Let me add one comment on that, please.
Yes.
So the adapter is it's a very important module in this setup, as the one who raised this question mentioned. So it's very important that this point is grounded if there's a malfunction in the adapter, and for that reason we have these spark gaps, two spark gaps built in at 600 volts to make sure in case of any failure in the bushing that this point is grounded properly. That means that no catastrophic result will happen due to our installation. So that's absolutely guaranteed, and we have never seen such a case in the past with our adapters. No problems like that.
Maybe here I have to admit that for me the adapter was just the BCU. But yes, I completely agree with what Marcus has mentioned. Very important, yes.
Next over to Marcus. How does gating work?
Okay, gating, yeah. We have seen on one of the slides the disturbance antenna or a CT that we use to pick up external noises, noise pulse signals from ground sheets or from radiation, from corona, from overhead lines. And these pulses are brought to a separate input of the instrument. So it's a special analog circuit that is separating these pulses from the measurement pulse. So whenever such a disturbance pulse appears in the system, a gate, so-called gate, is opened on the measurement pulse and is then rejecting this disturbance pulse from the measurement pulse. It's a very simple analog circuit, but that works for disturbance signal with, let's say, relatively low repetition rate. If we see disturbance signals of very high repetition rate, then we go into a different spectra of the measurement. So the instrument offers different ways to get rid of these external disturbances.
All right, thank you. Mihai, did I understand that your line of products will detect PD prior to chemical analysis reflects internal issues?
Yeah, so we understand that partial discharge within a transformer, those sparks, very, initial sparks within the insulation, together with, of course, the behavior of the paper, are generating explosive gases. So I will say that before high level of explosive gases is being measured, partial discharge appears first. In many ways, partial discharge being the cause of such, the existence of such explosive gases. So I would say yes.
Yeah, and one more failure case we have on bushings. If failures happen in, let's say, cracks in epoxy of the bushing, they will not show up in the DGA, but they can be measured by PD technology. That means with a partial discharge measurement technology and monitoring, we will see even more failures and issues on transformers than with DGA, which are show up only failures related to oil or close to oil, so that the PD produces gases. Next question, Michael.
All right, yep. And while I have you, Marcus, then, what is the interval of online measurements, and do I have to be on site to view the information?
No, there's no need to be on site to view the information. As Mia did show on a few slides, we have this remote communication module to the instrument via a mobile network. We are remote control over the local network of the substation. So we can check all these values from the control room and the substation or in the office of the utility. We can we do these kind of remote measurements here from Aachen also for some of our customers, and we take measurements, do consulting remotely. And on-site testing is done if we see some serious issues and we would like to go on site to take some in-depth measurements with maybe some additional equipment.
And maybe to complement that, PDX as a company has a service department, and the service department has a variety of, let's say, big tools that are used for such kind of testing. In fact, next week we are doing such testing in Italy on a particular transformer that was requested by the customer to have additional tests.
Thank you. Next question, I'm sending over to Mihai. Mihai, do you have any case studies demonstrating an alarm and save with the system?
Yeah, here by save, I'm interpreting the fact that by issuing an alarm, effectively we did in-depth partial discharge analysis, and that basically eventually showed that the transformer had a serious problem. And yes, we do have such examples. We can share them with you. Please email us. You have our contact, and we can set up a conversation. I think this is a very valid and interesting point to learn about. So whoever asks this question, please actually contact us.
All right. Next question is going to be from Marcus. Marcus, do you require reference voltage, and does it support DNP3?
So the reference voltage is taken from the bushing coupling unit as well. So this small box on top of the transformer close to the test that provides the PD impulse signal plus the superimposed voltage signal. So it's a capacitive divider built up between C1 of the bushing and CD built in with this box. So we see a 60 volt or ideally 60 volt AC signal on this output that is then brought to the instrument to show PD pulses in its correct phase position. So we can do voltage measurement with the same equipment, and I do not understand this. Does it support DNP3? So this question in this context is not clear to me.
No, I think this is a separate question, and I think we are supporting 61850, and we focused because of our OEM customers, to be honest with you, on 61850. They have not requested DMP3. I know that our North American customers may want to have DMP3. We are willing, based on a conversation, to evaluate what will mean to install a DMP3 stack. But at the moment, the system supports 61850.
I remember a project in the past in Mexico many years back where we implemented DMP3, but that was one installation in Mexico many years back. So in principle, yeah, we are flexible enough to find out if we can offer such an interface as well.
All right, thank you for that clarification. Next to Mihai, would it make any difference if this is applied to air core transformers?
Okay, so first of all, we should remind everyone that our company, Partial Discharge PDX Diagnostics, is basically looking at a variety of assets. Transformers are just one set, but we have rotating machines, we have cables, we have GIS switchgear. So the answer to this question, no, it doesn't make a difference. We are looking for partial discharge in general. Wherever partial discharge is present that we can tap into the way we described with our sensors, etc., we are going to find it, and then we will declare the severity of it, either via alarms or via more in-depth trends and patterns.
All right, thank you very much. Next, Marcus. How effective is the monitor detecting failure in composite bushings? Do you have any successful cases you could share?
I know we did find failures in composite bushings in the past, some of them during factory acceptance tests, some of them at site. The signal we receive from the bushing is similar to the signal that we see from a calibrator signal. So we can see from the spectra and from the pulse shape analysis of the PD signal where it comes from approximately. And by doing so and by comparing the amplitude also with the amplitude from the other phases, we can find out from which bushing this PD comes from. To answer this question shortly, yes, we can detect, and we did so in the past.
All right, thank you. Next, back over to Mihai. Is it possible to monitor the bushing tan delta and capacitance through the bushing tap adapters?
Yes, for sure. So we have two outputs. So from the bushing couplers, it goes into adapter with one Teflon lead. And from there, we have two BNC connectors, and one is used for PD measurements, and the other one exactly for tan delta capacitance.
Yeah, and we have some customers, they combined our PD measurement with a tan delta device from a different brand. And for that reason, we have on the PD output a PD plus superimposed AC voltage signal, so that the second output, the plain voltage output, can be used for a tan delta measurement device. And I know from customers in the US, they did so in the past. So yeah, it's possible. And then for that reason, we designed this BCU2D. So that's the difference between BCU2C and BCU2D. Yeah.
Yeah, I mean, for sure, we encourage customers to buy all devices from us. But as you can see, we are sufficiently open-minded and reliable. And also, we are encouraging proper testing of and monitoring of transformers. For us, this is our life. This is more important than trying to narrow and corner down a customer to just using a particular device from us.
All right, thanks a lot. Our next question is going to be for Marcus. Marcus, what is the benefit of using a quadrupole or Hfct as a coupling unit?
Okay, the quadrupole is designed as a standard RLC circuit with direct coupling, similar to the decoupling you use in the factory for factory acceptance testing. It provides a little bit higher sensitivity compared to the indirect measurement through inductive HFCT. With the HFCT, you have the galvanic separation of the output from the input. Some customers prefer to have this galvanic separation here on the PD output, and for that reason, you can decide at site by opening the lid of the box which kind of decoupling method you choose. There's a switch, a jumper on the box, and you can switch between two different modes.
All right, excellent. Next question is also going to be from Marcus. Is the bushing coupling circuit a capacitive or resistive circuit?
Capacitive. So the divider capacitor is capacitive.
Awesome. Next question is also going to be for you, Marcus, then, since you went through the last one so quickly. Will the bushing adapters need removal for routine power factor or tan delta testing? If so, what precautions are needed for reinstallation and verification for proper operation of the sensor?
Not necessarily. So it's not needed to remove the adapter and the coupling unit if you take the output from the box. But I presume it's a question about offline tan delta testing. For that, you can remove the coupling unit and you leave the bushing adapter in place. So you can use the output of the bushing adapter, but and remove just the end connector, the cable from the bushing adapter, and put your different device here.
All right. I'm going to send a question over to Charles to shake things up. Charles, how do we differentiate whether PD is from a bushing or a winding?
So Marcus had touched on this a little bit before, and basically you can tell by the pulse shape analysis, as Marcus said, if you have PD from the bushing, it'll look a lot like the calibrating signal. You can also tell by testing at a bushing whether or not it's coming from that bushing. Obviously, if you test from the other, that you're not going to get the same pulse shape or intensity. Also, as Mihai had mentioned in his presentation, there's several different sensors, and you could use acoustic sensors also to help locate defects within your high voltage asset. So just basically by analyzing the pulse shape and where you're testing from, this will help you to identify the type of defect and where that may be at. And again, looking at the phase resolve partial discharge pattern, or the FEQ-in pattern that Mihai had shown on several of his slides, that really gives good indication into like I said, the type of defect and where that may be. And that can be followed up by other testing methods, again, maybe acoustic or so, to actually try to find out where that partial discharge defect may be at.
Thanks, Charles. We have time for one last question. I know we went a little bit over, but we have one last, so why not? So Mihai, how long should one monitor the DUT to get a reliable diagnostic? Weeks, months, years?
Okay, so this is a very interesting question. So the reliable diagnostic is being obtained very quickly. So even in factory acceptance tests or otherwise, after setup, which can be hours, a test for about 2-3 hours will get us clearly a diagnostic. Do we have, and to what degree and where, and so on and so forth. That can be done both online and offline. The question is, how long should we monitor? I mean, if the transformer is just healthy, there will be no partial discharge or no significant partial discharge to be examined. So we need to have an online monitor that sits there from the inception, meaning from the moment the transformer has been installed, all the way to its end of life. You've seen the bar curve. So during the initial period, chances to find PD are higher than, let's say, during the middle life, and then towards the end of life, again, they are high. So generally speaking, transformer factories or power utilities that buy new transformers, they will install them right from the get-go. People that have had transformers in action for a lot of time, and I think in US and Canada this is the case, there are transformers there for 30, 40 years, I think they are a prime example where a monitoring device should go, because at any time we can catch early partial discharge and avoid any catastrophic failure. So thank you so much for the opportunity to actually answer these questions, and thank you for the questions, really interesting.
We really do appreciate these coming in. It makes our job very easy to sound smart when you guys ask such smart questions. But with that, it looks like we've run out of time. We apologize if we didn't get to your questions online, but we will be following with you offline. Once again, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But I'd like to thank you all once more for attending, and I hope you all have a great week.